All right, my friends, just one last piece to this lesson, a review of hyperbolas. So just the overarching idea here. So basically you could have, in this lesson, you could have hyperbolas that either open horizontally or vertically. So hyperbolas that open horizontally would be of the form x squared over a squared minus y squared over b squared equals 1. This subtraction is evidence of the definition of a hyperbola being the set of all points in a plane such that the distance between a point and two fixed points called foci is always the same constant value. So the difference part shows up here. Again, there's a big, long, grungy algebraic derivation that I've got available on the pre-cal video if you're interested. But the point is this, it looks just like the ellipse except it's got a minus. And then if the x squared term is positive, then it would open in the x direction. It would open in the y direction if the y squared term is positive. Okay, now your textbook is likely to be super picky about where the a and the b terms go. I personally am not as picky with how you write that, okay? So now there's a Pythagorean identity for hyperbolas, and it is c squared equals a squared plus b squared. And just like with ellipses, the absolute value of c is still the distance between the center and I'll say each focus. There we go. Okay, so this is the main idea. The equations that I have written here are for if a hyperbola is centered at the origin, and then we know shifting rules, so it'd be really easy to know what to do if they're shifted off the origin. Okay, example 5. The directions are just to graph. Part A, let's give you the quantity y plus 1 squared over 25 minus the quantity x minus 4 squared over 9 equals 1. Super good time to pause the video. But here's my solution. First of all, I can tell it's a hyperbola because you see the subtraction here. It's already in standard form because you have equals 1, you have squares completed, and you even have little cute perfect squares down here. You can tell that it opens vertically since your y squared term is the positive one. It's centered at positive 4, negative 1. Let's see, positive 4, negative 1. About like that. 1, 2, 3, 4. Negative 1. Let's move that to here. There we go. Okay. So 25, of course, is 5 squared. So you're going to go up 5 units. 1, 2, 3, 4, 5. Down 1, 2, 3, 4, 5. 9 being 3 squared. Helps you to go 1, 2, 3, 1, 2, 1, 2, 3, I think. Okay, boundary box for hyperbolas, necessary, not optional like they were with ellipses. Okay, so you draw your boundary box. It should go through all 4 points that you have there. For a hyperbola, the next thing that you will draw is asymptotes. They should go from corner to corner on your boundary box. And I'm now realizing that my spacing is not good. Okay, last thing, the hyperbola, we said it would open vertically. Your hyperbola should be tangent to your boundary box. your hyperbola should approach the asymptotes. And as a matter of fact, a hyperbola starts thinking that it is basically just kind of two intersecting lines as your x and y values get large in magnitude. There we go. So that's that. So a little more challenging, part B. Give you one guess as to what I'm going to do to make this a little more challenging. 9y squared minus 4x squared plus 54y plus 8x plus 78 equals 0. All right. Again, pause the video, do what you can, check with me in a little bit. So let's diagnose this. How do I know it's not a parabola? Because I can see degree 2 on x and y. How do I know it's not an ellipse? Because your squared term for y is positive and your squared term for x is negative. So I'm definitely expecting a hyperbola here. So I'm going to go ahead and combine like terms. So 9y squared and 54y. I'm also going to factor the 9 out. The x terms, negative 4x, and negative 4x squared, that is, and 8x. I'm also going to factor out the negative 4 there. And then the constant term, I'm going to move it to the other side of the equation. Okay, completing the square, divide 6 by 2, square the results. Your magic ingredient is 9. It looks like I added 9, but I actually added 9 nines. So I'm going to add 81 to the right side to balance the equation. I'm going to divide by 2 squares, so magic ingredient is 1. I just actually subtracted 4 ones, so I could subtract 4 from the other side to clean that up. So now we've got 9 times, whoopsie, let's complete the square here. What would that be? Y plus 3 squared minus 4 times x minus 1 squared. And then on the right side, what is that? 81 minus 78 is 3, minus 4 is negative 1. Now the negative 1 gives some folks a bit of an uh-oh moment, but we know how to turn that into a positive 1. You could multiply or divide by negative 1, okay? So now what do I have? I have negative 9 times the quantity y plus 3 squared plus 4 times the quantity x minus 1 squared equals 1. And come on, that's adorable. At first, it totally looked like this thing was going to open in the y direction, but now a little switcheroo, all of a sudden it's going to open in the x direction. What to do about the 4 and the 9? First of all, I really like my positive terms to be first. So you're going to see me write this over here. I'm going to write it as x minus 1 squared divided by 1/4, and I hope that makes sense. Dividing by 1/4 is the same as multiplying by 4. And then I'm going to have minus the quantity y plus 3 squared divided by what to be the equivalent of multiplying by 9, divided by 1/9 equals 1. Just to be clear, 1/4 is 1/2 squared. 1/9 is 1/3 squared. And then we can go ahead and graph it. So this thing is shifted, let's see, to the right 1, down 3. I'm going to make my scale kind of big. Not that big. Maybe, I don't know. So, to the right 1, down 3. Okay, and then from that center, we're going to go to the right half a unit and to the left half a unit. And then from that center, we're going to go up 1/3 of a unit and down 1/3 of a unit. Boundary box. Asymptotes. Make sure your asymptotes always go through the center and then also the corners of your boundary box. And then which direction should this go? When you got it into this kind of completed square form, or standard form, I should say, your x term was positive, and so that means your hyperbola will open in the x direction. And please remember, your hyperbola should be tangent to the boundary box. And your hyperbola should have asymptotic behavior, as in your hyperbola, if you were to cover up the middle part, your hyperbola looks like just two intersecting lines if you were to cover up that middle part there, okay? All right, my friends, I hope that's making sense. Example 6. Let's have you find the equation of each asymptote. From, let's just do example 5, part, I guess, what do you want? Part A or B? Yeah, I'm all by myself. Let's just do part B, just for fun. So let's see what we do, okay? Now, if you look in the book, you're gonna find this like unnecessarily fancy looking formula for this. But I hope, dear calculus students, that you realize that when you're finding equations of these asymptotes, you're literally finding the equation of a line graph. And so you're just gonna do a little algebra 1 on it and be done. So let's think. So this line right here, this asymptote, what's its slope? You know, how far up and how far over did you go? So I'm gonna make a note of that. So your slope would be your rise, you went up 1/3. Your run, you went over 1/2. There you go. Flip, multiply, you end up with 2/3. There we go. What's the slope of this line that goes, you know, your rise would have been, I guess you could think of your rise as -1/3 and your run as +1/2. The slope of this line would have ended up being -2/3. And then let's keep everybody from working too hard. Both lines go through that center point. I've had people carefully find the coordinates of the corners of the boundary box. But my friends, both lines go through the center, and the center was at the point 1, -3. So if we were to just point slope this sucker, we'd be done. So the equation of each asymptote, so the one that goes up and to the right would be y plus 3 equals the slope times x minus 1. And then the line that goes down to the right would have been y plus 3 equals -2/3 times x minus 1. And I hope it makes sense that because these two equations look the way they do, it is a-okay to write the answer as y plus 3 equals, that's right, plus or minus 2/3 times the quantity x plus 1. You could do either one, but I think most of us like this little condensed version the most. Okay, all right. Just algebra 1, my friends, please, nothing fancy for that. Okay, example 7, and the last example of this lesson. Find the coordinates of the foci for example 5, and then let's look at part A for this one. Okay, so first thing you need to know is what is the Pythagorean identity for ellipses. It is c² equals a² plus b², and because you're not subtracting in this one, it doesn't matter what you put in for a² or b² is essentially as far as which one's bigger or what have you. So here is what we had for part A. So you could solve for c. You could 5² and 3² go in either place. It doesn't really matter. So c² equals, sure, 5² plus 3². So c² is 34, I think. And so c would be plus or minus √34. Now this is all fine and dandy, but it won't do you any good if you don't know what C actually tells you. Remember, absolute value of C is the distance between the center and each focus. So in that case then, and I know it's been a while here, but I hope it makes sense. Your focus would lie somewhere along this axis of symmetry here, and your hyperbolas will always open toward your foci, okay? And then C is the distance from your center, which let's label, in this case, the center, what was that, 4, -1, it looks like. And so in this case, you would be going up from here, you're gonna go up square root 34 and down square root 34 units to get to the foci. So this focus right here would have coordinates still 4, but -1 plus square root 34. And then this focus would have coordinates 4 and then -1 minus square root 34. There we go. Okay, so to be clear, your foci would be at 4 and then -1 plus or minus square root 34. There you go. And you could certainly be more formulaic about all this than I am, but I feel like the pictures are the most clear way to go about it, and it would help you minimize the amount of memorization that you need to be successful with this stuff. All right, my friends, I hope this is helpful to you. That's the end of section 9.1. Again, I do have more detailed videos that I'll include. They're optional. If you want to watch them, you wouldn't need to take notes unless you wanted to. But this is the review, just a general overview for conic sections. How to graph them, find their foci, directrix, and equations of asymptotes where appropriate. All right, take care, everybody.